So in the last video we discussed how the operations of joining paths and reversing paths interact with homology. Now I want to discuss another kind of thing, which is about how homotopy of paths interacts with homology. Okay, so suppose we've got two paths. And let H be a homotopy between them. So yeah, you've got H of naught x, H naught x is going to be u of x, and H of 1x is going to be v of x. Okay, so yeah, we can kind of indicate this by drawing a little diagram like this. So you've got your t is running this way, and your x kind of is running this way, if you like. So we can draw an h here. What we're saying is that when t is 0, in other words, on this edge here, we've just got u, and on the right-hand edge, where t is 1, we've got v. But there's also kind of two other paths implicit in this picture. You know, there's the path kind of going along the bottom here, which we could call m, and the path up here going along top, which we can call n. So in formulas, m and n. So these, well, think of these as being again defined on the one simplex. So m of m of t naught t1. Okay, so we're thinking this kind of looks more like this is the unit interval, so we're thinking about it parameterized by t1. So this is going to be h of t1 e naught. Okay, that's what we get kind of along the bottom here, right? This is this vertical direction is supposed to be the one simplex, so it kind of goes from e0 to e1, as it were, whereas this is kind of the unit interval going from 0 to 1. So that. And then similarly, n of t naught t1 is just h of t1, e1. Okay, so we've got these four paths that are appearing in this picture. And we've also got some two simplices appearing in this picture. You see, we can split the r square across the middle like that. So let's define this. Let's call it Q, say, from no, we've got two maps, so let's call them P and Q. From delta 2 to x. Okay, so let's say the P is kind of like the bottom half, and Q is going to be the top half. So we're going to have P of T naught, T1, T2. So it's going to be H, or H is going to be, we have to apply it to this kind of bottom simplex here. This is bottom simplex here has, the vertices, this is kind of 0, comma E naught here. This is 1, comma E naught. This is 1, comma E1 up there. Okay, so what we've got is like T naught times the bottom thing, the bottom left corner, which is 0 E naught, plus T1 times this one over here, which is 1, comma E naught, plus T2 times 1, comma E1. So if you like, so in the first corner you've got your T naught, and T1 and T2, and in the second corner here you've just got your T naught plus T1 and T2. and your Q is going to be the top half. Okay, so this is do this in a similar sort of way. Again, okay, so we've got one vertex here down at 0e0, and then the next vertex here is going to be at 0e1. And the last vertex again up at the top right corner, 1e1. Okay, so this is h of, looking at the first corner, we just get a t2. And then the second thing here, you've got t0 e0 plus t1 e1 plus t2 e2. So that's so t2 e1. So that's t0 t1 plus t2. Okay. So that's what we get for this picture here. Okay. Then okay, so then we're gonna look at p minus q. So we've got this p minus q here. So what's the boundary of p? Okay, so you just get this kind of three things around here, right? So the first one is your v, right? You omit the zero, this bottom vertex here. What you're left with is v. Then minus the thing that you get by sort of omitting this vertex, which is the sort of diagonal thing of the square. Okay, and then plus the last thing that you get is omitting the last vertex. That just leaves you with the path m. So that was what you got for p. Then you do it for q. Okay, so omitting vertex 0, that gives you n. Sorry. Yeah. No, in this case, we get an n there, and then you get minus, again, the middle thing is the diagonal. And then the last thing is your u. Okay, and the diagonal things cancel out. So what we get here is v plus m minus n minus u. Okay, so that's our conclusion. So maybe let's just kind of write this in a box up here. That you get v plus m minus n minus u is in b1x. Okay, so now we've got this general relation. We've got a homotopy h from the path u to the path v, and then we've kind of got so we've got this homotopy. You've got the path u sort of moving to the path v, and you trace out how the beginning of path u moves as we do the homotopy. That gives us this path m. And if we trace out how the end of the path u moves as we deform it to become equal to v, that gives us this path n. And we had this conclusion that modulo the boundary group, v plus m minus n minus u is going to be equal to 0. And there's two special cases of this that we want to discuss. So special case 1 is what I'm going to call a pinned homotopy. This is where u is a path from A to B, and v is also a path with the same endpoints from A to B, and h of t e0 is equal to A, h of t e1 equal to B for all t. Okay, so the situation here, you've got your path u and your path v. They kind of Here's your A, here's your B. U is like this, say. V is like this. And our homotopy H, it deforms U to V, but all the time it keeps the endpoints pinned, right? So each at all, it's like a movie deforming U to V. As we do the deformation, the endpoints always stay equal A and B. Here, the conclusion. What this means is that the path M is just the constant path at A, right? Because this is M is telling us how the initial point of view moves, and it doesn't move at all. It stays at A, and N is CB. Therefore, M and N are both in B1X. So this this relation star up here becomes. We can ignore the M and the N. It just tells us that V minus U is in B1X. In other words, the cosets V plus B1X, U plus V1X, and V plus B1X are the same. Okay. So conclusion from that is that a pinned homotopy between paths doesn't change the homology class. Okay. And the second special case this is going to be the loop homotopy. This is where U and V are loops. Okay, so both U and V are loops. So the kind of picture here is more like here's U and here's V, and we deform it. Our homotopy H, it deforms U to V, but it always does loops, so H of T naught is HTE1 for all T. Okay, so that means that this is like we've got a movie from one loop to another loop, but at all times in the movie it's still a loop. Okay, still a closed loop. And so that's what we mean by a loop homotopy. So that means that M equals N. Okay, so right, the idea is if you this is kind of the path that you get at time t is taken by this slice through the homotopy, and it's supposed to be a loop, so M of t and N of t are supposed to be the same. Okay, so so in this case M equals N. In that case, this relation star here, the M and the N are the same, gives V minus U, again in B1X. So in this case, U plus B1X is V plus B1X. Okay. So notice here in this case, because U and V are loops, UE0 equals U equal 1, that means that the boundary of U is 0, and the boundary of V is 0. So U and V, they both lie in Z1X, and so these are genuine homology classes. They lie in Z1X mod B1X. So we can say that U and V are the same in homology. So those are the kind of key points about the interaction between homology and loop path homotopy.